What do you have a blood donation swimming pool? You can take the sea from USC. Yeah, I know that. I feel like, oh, after school, oh, I see the view of the sea. It's so cute. Sir,
Yes.
what are your university? Which university did you go to? My idol. You went to Senpai. Senpai.
Okay, let's continue. Okay.
What test? Flame test?
Right. Okay. So, have you all finished the organic services?
No.
No. Okay. But then I have uploaded the homework, the answer to that homework, which you can all check out. And let's tell me back if you have got any question about those answers. Okay.
So, new chapter?
And we will start the important organic compound chapter today. Yeah, okay. So there are a few important organic compounds that you should know. The first one is aspirin. Does anyone here take or know what aspirin is? Do you take aspirin?
It's medicine.
Sometimes. What is it?
Painkiller.
It's a painkiller, but it's known also for its other uses. Okay. So first, I want you to put down aspirin. Okay. So aspirin is the first important chemical. This is a painkiller which has additional properties such as antipyretic property, which means it prevents or it can make the fever symptoms go away, you say. So which has additional properties. Its main function is being used as a painkiller. So other functions include it is antipyretic. So this word is very difficult for you. So just say anti, it fights fever. It fights fever. If you're having a raging fever, you can take this pill or drug and it can help make those symptoms go away. Okay, fight fever symptoms. If you have fever for too long, you can fry your brain. Quite literally. Okay, you know the enzymes in your brain, okay? Having a very, very high fever for a long time will denature those enzymes. So the second use of aspirin is that it is anti-inflammatory. Okay, so anti-inflammatory, which fights inflammation, of course. So inflammation, and most important of all, many people take aspirin not because of these two properties or its main painkilling property, but because of its blood thinning property. So why would people take something to thin their blood? So blood thinning means it makes blood less viscous. So can you tell me, especially for those doing biology, why would a doctor want to give a drug, to a patient that will thin his or her blood, that will make the blood less viscous? Prevent blood clot, and most importantly, for those who recover from a heart attack, they may have some like a very thin blood vessel. So by making blood less viscous, they clot less easily, and it will be less likely for these people to get a second or third heart attack. So put a star here. That's because when blood is thin, so you can write down, when blood is thin, it is less viscous. So it's less likely to clot. And heart attack is caused by a plaque, formed inside the vessel. So less likely to have subsequent heart attack. Right. So, but its main use is as a painkilling property. Now we look at the chemical structure, so you need to remember the structure, be able to draw it. You have CO, so COOH here, and then you have OC11OCH3. So OC11OCH3. So this is called acetyl salicylic acid. So this group, we call it the acetyl group. So acetyl. And then we have salicylic acid here. So this part, we call this the salicylic acid. But because this is such a long name, as you may have noticed, acetylsalicylic acid, we will just call it aspirin.
Sorry.
Yes.
The yellow.
Oh, okay, right. Don't worry, the yellow thing is just to write it out. Okay, maybe I'll write it in orange, sorry. Salicylic acid. Just know how to recognize this word because in exam you can just substitute it with aspirin. The word aspirin. Aspirin means the whole thing combined. The yellow, now I'll make it orange. The orange and the green part combined. It is an acid because of one of the functional group. So I want you to identify all the functional group present in this molecule, which is what they will do in the exam. Let me make this a question and all of you can answer. Question. Identify all functional groups present in this molecule. Tell me what you see. Yes, but we call it a carboxyl group. Okay, so this is a carboxyl group. Yeah, but it's fine if you just call it carboxylic acid. But we'll write it properly as carboxyl group. Just like you don't call OH group an OH group, you call it hydroxyl group. Okay, yeah, but it's okay. We can write hydroxyl and draw COOH. What else do you see other than the carboxyl group, which is found up here?
Ester.
Ester. So the ester is the COO group. Okay. So I think press the recorder. I think yes, it's recording. So number 2, we have the ester group, which is COO. Yeah. Don't confuse ester group with the carbonyl group in ketone. Okay. So C-double-bond-O is a ketone group. C-double-bond-O-O is an ester group. Okay, I see many students confusing these two, so don't be one of them. So this is the carbonyl group in ketone. This is the ester group in ester, of course. So this is the ester group in ester. They are certainly not the same. They look similar, but they are not the same. And then the carbonyl group is also not the same thing as the aldehyde group. So this is the aldehyde group, which is found in aldehyde. Yeah, you may be wondering why I'm writing things twice here. That's because this is the name of the family of the compound. This is the name of the family of the compound, and this is the name of the functional group. So they're different. Okay. Yeah, and these three, I know their similarity. Okay, they look very similar, but they are not the same functional group. Okay, they have share a lot of similarity. The third and the final group. If you see a single double bond, you could be right. But what do we call? We also do not call it a benzene group. We call it a phenyl group. Okay, yeah, phenyl group means a benzene ring as part of the structure. You know what's the difference between a phenyl group and benzene? Benzene is a standalone structure. If you see a single hexagonal ring with 3 double bonds, nothing else attached to it, you are right, it is benzene. Because it actually has got 6 carbon and 6 hydrogen. You see at these positions, these are the hydrogen. So you have C6H6. But benzene should not be confused with the functional group phenyl group. Because the phenyl group is, if you think it looks like a benzene, yes, because it's actually a benzene, but it is attached to something else, which means it can only have how many hydrogen? If this must be attached to something else, that means this is not available. 5, only 5 hydrogen. So they only differ by 1 hydrogen. Yeah, so this is C6H5, and because it's a group, you know a functional group has to be attached to something, so there's a stick here. So we call this a phenyl group. They are not the same thing, okay? So you have C6H5, and you can draw this line in there. A group has to be able to connect to something else. So whenever they ask you to draw a group, I want you to show a line there in your answer. Don't just write COH without showing a stick here. A group has to be attached to something else. Okay, so draw it. Right. Now, we just learned the acetylsalicylic acid. Okay, they may ask you for some reactions. Okay, that acetylsalicylic acid can react or take part in. Okay, for example, they can react with sodium hydroxide, and this part of the molecule it will react. Okay, so can you draw this again? The acetyl salicylic acid, you have COOH. We can now condense that very large and bulky group COOH into just COOH. We call this condensed structural. This is the full structural, you can say. And then we have OCO, so COOCH3, like that. Okay? So when you add sodium hydroxide, do you all remember what the reaction is like when you react HCl with NaOH? What are the products? Salt and water. What is the salt? NaCl. Okay. But I recommend that you write out also the charge, because when you do, you can see like that this is an ionic compound. This is an ionic compound. Now this is also an acid, just like HCl. Maybe I can show you where the H and the Cl come from, or where the OH come from. So this is the H and the OH. They together combine to form H2O. So now I want you to apply. You see an H in here. Can you tell me what happens when I react this very like strange looking thing with NaOH? Can you show me the product? It will not be NaOH.
COO minus Na.
Yes, COO minus Na plus. So can you copy the whole thing? Remember I said the other parts, they don't take part in the reaction, but they will become a negatively charged COO minus ion, and then you have an Na plus charged ion. So this is a salt, okay? You have also water formed as a result. Why would anyone want to do this? Do this reaction. It makes aspirin more soluble. So this reaction, when they ask you what does it do, you can say, well, this reaction makes aspirin, so this is called aspirin on the right. This is a soluble aspirin on the right. So aspirin on the left, soluble aspirin on the right. Why do we call it soluble aspirin? Because it's just like sodium chloride. You know sodium chloride is soluble, right, in water. By turning this molecule, which is no ions, into something with ions, we greatly increase the solubility. And this is important because, let's say you have very serious headache, or for the ladies, you have like maybe the monthly, nightmare. Like these aspirin, you want them to work fast. Okay, by making them more soluble, they can go into your blood more easily, reaching the target organ more easily. So write this down. This reaction, when they ask you what's the purpose, makes aspirin more soluble. So they can dissolve in blood. Yeah, because you're turning it into an ionic compound. So turn into ionic salt. Okay, just like NaCl. So like NaCl. And because NaCl is soluble aspirin is also pretty soluble. So the next point is it can dissolve in blood more easily. And exert its effect more easily. So exert its effect, the painkilling effect, more easily. Right. So, and just one more word I want to share with you is sometimes they don't use the word painkiller in the exam. They will use another word with equivalent meaning. It's analgesic, okay? ANALGESIC, okay? So just recognize this word. I don't need you to spell it, okay? So it is an analgesic. So, so this is an analgesic, which means it is a painkiller, which has, it is just a painkiller, yeah. And then these are the 4 properties, remember that. Aspirin, right? And other than aspirin, okay, are there other molecules that we need to know in the DSC chemistry? Of course, there is. The next thing is what everybody should use. You may not use aspirin, but you will definitely use detergent at home, right? Yes. Detergent, okay, or soap. Okay, so we'll turn our attention to soap next. So, but before we move on, I want all to work on this for 30 seconds. Show me what the molecular formula is for aspirin, because I think some students will count incorrectly. So I want to hear about the molecular rate, yes, formula, or yeah, you may copy this onto your diagram, and then in 30 seconds time we'll check the answer. Show me the molecular formula. Your molecular formula means the total number of carbon, hydrogen, and oxygen in this molecule. Because I think some of you may miscount the number. So you have 30 seconds. Yeah, maybe it's best that you count it on the paper, because now you will very easily lose track. Okay? 30 seconds. Be careful when you see the CC double bond inside the phenyl group. Okay, because right. So let's check the answer. How many carbon do you think there are?
9.
9. Yes. So if you're unsure, you can let's count together. 1, 2, 3, 4, 5, 6, 7, 8, 9. So C should be relatively easy to count. What about hydrogen?
8.
Yes, 8. You have 1, another 3 which gives 4, and then you have 5, 6, 7, 8. There are no hydrogen at these 2 carbons as they are fully bonded. They are maximally bonded to 4 partners. So H8. And finally, how many O?
4.
4. Okay, O4. So if you don't know the molecular formula, it will make the determination of the molar mass impossible. Okay, so make sure you don't miscount the number of hydrogen. That will, throw your answer off. Okay, so that's molecular formula. Just a short exercise here. We will now turn our attention to detergents. So what are detergents? Of course, everybody knows detergent, but the definition of a detergent is that it is something that improves the cleaning property of water. So improves the cleaning property of water. So this sentence may sound strange at first, but if you have seen water droplets on a lotus leaf, have you seen water droplets on a lotus leaf before? What is the appearance of water on a lotus leaf compared to on an ordinary surface? It rolls up into a ball. Have you seen that? Yeah, so this is the lotus leaf. The reason why water does this, okay, you can try, but don't hurt the lotus in this process. Okay, you can find some hydrophobic spray. You will find these hydrophobic spray from the sneaker shop. Okay, that you can spray on any surface. It will make the surface hydrophobic. The surface of the lotus leaf is hydrophobic. It means water hating. So some of you may have heard of different types of phobia. So claustrophobia, for example, okay, the fear of staying inside a confined space. So phobic means hate or the fear for something. And then you have this water droplet here. Hydro means water, and if it hates water so much, water will want to minimize its contact with this surface. This is why on ordinary surface, okay, water will spread out. Yeah, you can try to put some water on your table right now. Because you did not put any hydrophobic surface on the table, water will spread out because the surface don't particularly hate water. However, if you get one of those like a hydrophobic spray from sneaker store and you spray this surface so that it becomes hydrophobic, water will want to minimize its contact with the surface. This is why it rolls up into a ball. Can you tell me how much surface is water like having with the green surface? It's this much, right? But when it rolls up into a ball, you know how circles touch a line, right? It only interacts at one point. So this is why, you now know the explanation, why water would roll up. Okay, so water would roll up into a bit or ball on hydrophobic surfaces like lotus leaf. So hydrophobic surfaces like lotus leaf. And this is a perfect example for illustrating the fact that, well, water may not be able to clean things very well, especially when it rolls up into a ball. So how do we improve that? We can add at detergent. So can you put down two description here? This is a hydrophilic surface. So philic means love, okay, and hydro means water. This is water loving, okay, this surface. So water loving surface. We can understand this word literally. And this is a hydrophobic surface, which means water hating. When you put water on a water hating surface compared to on a water loving surface, water will spread out. Okay, so we say water spreads out. And then we say here, water forms a bead. So bead, okay, so B-A-D. Now, the next thing that we need to discuss, okay, that detergent can help, solve, okay, is the surface tension of water. So you may have heard of this term in either physics or biology. So in biology, you may have seen this insect before that can walk on water, like Jesus, okay? But actually, it can do that because its legs is interacting with the skin of water, okay? Yeah, this insect, okay, can walk on water. So this insect called water strider can walk on water, okay? It's called water strider.
How can you draw so nice?
Yeah, because there is something called surface tension. So a surface tension is like the skin of water. So surface tension, which is kind of like the skin of water. How does this form in the first place? When you have no detergent added, when you have a lot of H2O molecules here, okay, so for this, maybe I will just copy this a few times, you have a lot of H2O. What is the name of the strongest intermolecular force formed between water? Hydrogen bond. You know, hydrogen bond is pretty strong. The hydrogen bond causes the water to, stick onto one another very tightly. So it's like a bunch of people holding hands. It's very difficult to, separate these people. If you try hard enough, of course, you can break through, okay? But then, how can we make these people interact less strongly? So think of this as like people holding hands. Okay, if you have many people, they can hold like hands to form a very strong circle. Yeah, this is without any detergent. When you do not add any detergent, you see we say the surface tension is strong. So there's strong surface tension. Okay, you know the word tension is used to describe the force that exists in a rope. If let's say like I'm holding out a rope and I connect to you using that rope and I'm pulling on that rope, there will be tension in the rope, right? So in this case, it's similar. It's just that there are these invisible ropes between the H2O that holds them together. So we call this surface tension. There's strong surface tension. What will happen if we add a detergent? Okay, a few drops of detergent. Don't try this on this insect. You will drown it. Okay, because as soon as you put a few drops of detergent in here, this lake will sink into water as it can no longer hold on to that anymore. Why is that? So we can understand the chemistry of this. So when you add a few drops of detergent, so detergent molecule, as you will see later, they look like tadpoles. They look like tadpoles. So what are they actually doing here? Let me draw it in this other direction, sorry. So they will do something like this. As they insert themselves between the water, does the spacing between water increase or does it decrease as you insert detergent molecule into the structure? Increases. When you increase the distance between water, you are weakening the attraction between them. You're weakening the hydrogen bond between them. So this is what happens when you add a detergent. So let's write down a few important sentences here. Okay, so number one, with detergent, the detergent molecule will insert itself among the water. So detergent molecules will insert themselves among the H2O. And what does this do? This would weaken the surface tension. So people people are holding hands less tightly now. So the circle, expand a little bit. And this is great if you are trying to clean a piece of fabric. Because imagine that I'm holding out a piece of fabric here. Okay, this is a piece of fabric with some ketchup stain on it. If you want to clean it, well, it's best that water spreads out, right? Because if it beads up, okay, like this, it will not be able to clean a very large surface. It will only be able to clean this surface. But if it spreads out, like you see, this is what happens when you add a detergent. It can wet a larger surface, right? Is that clear? Okay? So you can put down, this is what happens without detergent. It can only wet a very small surface. With detergent added, you're decreasing the surface tension and you're increasing the wetting power of water. So the wetting power of water. Wetting power, when we explain it in simple terms, it means it can interact with the fabric that you're trying to clean over a larger surface area. So over a larger surface area. So is that clear why we add detergent to the laundry, to the dishes? Okay, that's the first thing. Now we'll look at another property. Okay, put down a very short concluding sentence here first. We say detergent can improve the wetting property of water. On the next page, we will turn to another property of detergent, okay, known as the emulsifying property. If you do also biology, you have heard of a similar thing, okay, like detergent. It's bio, okay. Bio can also emulsify fat, okay. So we have a wetting property. Okay, what wetting property? Just singular, sorry. Right. Next up, we will look at the types of soap first. Okay, before we look at the second property. So, yes, you can copy this first. So, without detergent, water beads up. Okay, because of the surface tension. People are holding hands very tightly. With detergent, it's kind of like if these people they know one another, they will hold hands more tightly. But suddenly you're introducing a few random strangers, okay, in between these people who normally are friends. So then they will break, those friendships between them. They will hold hands less tightly. So that's detergent. Next up, we have the types of detergent. Any question on this page first? No. Okay. So on the next page, we look at the types of detergent. We have what we call soapy detergent and soapless detergent. So types of detergent, we have number one, soapy detergent, and then we have the soapless detergent. But I think this word is kind of misleading because the detergent you have at home, they are actually soapless detergent. But what happens when you put it under water? There's a lot of soap, right? So I kind of not like this term. Okay, so and put down what they are first. Soapy detergent, they are made from fat or oil. Okay, you know what? You can you can use the used cooking oil, okay, and turn them into soap by adding sodium hydroxide into it. So that reaction is called saponification. So there are some tutorials online that will show you how you do it. You will need very concentrated sodium hydroxide. So if you want to do that, be careful, okay? But you can totally turn used cooking oil. Let's say you finish frying pork chop, or I don't know what you like to fry. But then the used cooking oil, you have got no use for it anyway, right? You can then add sodium hydroxide and some lavender oil, or some herbs into it. It will turn into those hard hand soap. You have seen those hand soap, right? Not many people use hand soap anymore, okay, but they're actually better for your skin. So made from fat, okay, or oil, okay, by saponification. We'll get to this reaction shortly, but make sure you can spell this word, saponification, okay? Yes, this is actually alkaline hydrolysis, okay, it is a type of alkaline hydrolysis. You still remember when I introduced to you the ester, that fat is an ester. Yeah, you know fat is triglyceride made from 3 part fatty acid and 1 part glycerol. So fat is actually an ester, and saponification, okay, is a type of alkaline hydrolysis. So this word should sound familiar to you because we discussed this in ester reaction. Ester can be hydrolyzed.
I don't remember the name. I don't remember the reaction.
I'll remind you that later. By dilute sodium hydroxide, ester can also be hydrolyzed by dilute hydrochloric acid under heating. So the hydrolysis by sodium hydroxide, we call it alkaline hydrolysis. Then we have saltless detergent. They are not made from fat anymore. Instead, they are made from petroleum. So the salt, the dish detergent you have at home, is made from petroleum, made from oil. I mean crude oil, okay, not like the oil on the left. These, by oil, I mean animal fat and oil. These are natural, okay? So natural origin, which is why they are better for your skin. And these are, well, they are not natural, but they are like more organic compound based. Okay, so organic compound based, right? So they are made from petroleum by other reaction. So we will first look at how we can make soap. Okay, the reaction called saponification. So this reaction is so simple that you can do it at home, but it is dangerous because you're dealing with highly corrosive concentrated sodium hydroxide. So right now, what you need to know about saponification first. Number one, fats, okay, or oil are natural triesters. Okay, so natural triesters. This is because, okay, especially like I said, especially for those of you who do biology, you know, if this is fat, there will be 1 part glycerol. So this is glycerol, plus 3 part fatty acids. So to me, it looks like the alphabet E. So you have 3 part fatty acid. So write down the composition. Glycerol times 1 plus fatty acid times 3. Together, it makes fat or oil. So in biology, this is known as triglyceride. Okay, so triglyceride. So the chemical structure, unfortunately, you need to also know. Okay, so we'll draw the chemical structure of glycerol now. Is you need to know the name of this compound. I think I reminded you this when we discussed the naming of alcohol. What do you call this compound? I need the systematic or the IUPAC name.
The yellow, what is the name of it?
This is glycerol. This is glycerol, yeah, but we don't call it glycerol in chemistry, in organic chem. In biology, you call it glycerol. What is the systematic name of this compound using the IUPAC nomenclature?
Propane 1, 2, 3, 4.
How many carbons do you see? 3. What is the root of 3?
Propane.
Pro. What do you call an alcohol with 3 OH group? Triol. So put it all together, you have so close. Propane. At least I can hear the E from you. 1, 2, 3 triol. Yeah, that's because if you don't tell me that they are at 1, 2, 3 position, well, who knows? Maybe the 3 OH group they are on the same carbon, right? Yeah, you can't rule the possibility of somebody drawing a triol with 3 OH group on the first carbon. So you can't assume that I know they are on 3 separate carbons. So write out propane 1, 2, 3 triol there. Yeah, so that's propane 1, 2, 3 triol. And I forgot to add something in here, so you add it back. The glycerol and the fatty acid. Yeah, before I add these red lines, they appear like 4 separate substances. Actually, they are not. They kind of look like the alphabet E, don't you see? So like at distance, it looks like the alphabet E. Yeah, because they connect through ester bonds. Okay, so these are ester bonds. Which is why we say fats and oil, they are natural ester. Right, to show you what I mean by that, let me draw you some fatty acids. Fatty acids, you actually know them. Fatty acids are basically very long chain carboxylic acid. So very long chain carboxylic acids. What is the general formula of carboxylic acid? That's the functional group. CnH2n
Plus one.
plus 1
Oh.
COOH. Okay, so put this down. CnH2n plus 1 COOH.
Oh, right.
Yeah, by very long chain, I mean n is in the range of like 20 something. Okay, that's very long. You don't even know the root. I don't even want to know the root. Okay, yeah, you don't have to know that many different roots, because if the number of carbon gets to a very, very large size, we will just condense the formula into C something, H something, COH. We don't really like to address it by the name in that case. But don't worry, fatty acids are just very long chain carboxylic acids. So we will show that very long chain with these like lines to show that, well, indeed there's a very long chain there. So this is the fatty acid I placed besides the glycerol. Can anyone tell me what is the name of that reaction that will take place between the alcohol part and the carboxylic acid part? What is that reaction called? When you have a carboxylic acid and an alcohol, do you remember the name of that reaction? It started with E. Esterification. So can you draw this? This thing is actually RCOH. This thing is just the R prime OH. Yeah, so this is the R prime you see, and this is the OH. Okay, so you have the R prime and the OH. Remember what we remove between these two substances in an esterification reaction? Remove water. But the water is coming from the OH group of the carboxylic acid and the H of the alcohol. So together, these forms water. We call this reaction esterification. So can you all put this down? After undergoing esterification, okay, esterification, they will be turned into, you need to draw the resultant compound. What does it look like? Well, it's a little bit more complicated. Okay, let me copy this over. Yeah, unfortunately, you cannot copy it. You have to draw it. Okay, so we have these three groups. You see, they connect through the O to the glycerol, and they all, they have an ester group. Now you see, so this is the COOH. This is the COO group, another COO group, another COO group. Can you all see the ester bond in here? The reason why we call it a triester is because there are 3 ester bonds, self-explanatory. So circle the ester bond. Yeah, so circle the ester bond. So triester, because fat or oil, each molecule of fat, so this whole thing is a molecule of fat. Okay, each fat or oil molecule has 3 ester, which is COO bonds. Therefore, triester. So that's so good, right? Okay. But then, just like you learned that esters can be hydrolyzed by acid and by base, we can also hydrolyze this, okay, at home. So can you put down the name of this thing? So this is a fat or oil molecule. Oil, yeah, fat or oil. Fat and oil, they are really the same thing. It's just that they have different melting point. Fat, the name fat tells you that the melting point is higher. So you know animal fat, they are solid. But oil, fish oil, okay, they actually are just fat with a lower melting point. So they exist as a liquid. So on the next page, we look at really saponification. Yeah, that's not saponification. This is esterification. So saponification is the alkaline hydrolysis. Okay, so alkaline hydrolysis of fat by concentrated sodium hydroxide. So a bit of a review first. Okay, so we did this before. Actually, just 2 lessons ago, if I remember correctly. When you have an ester, do you remember what acid hydrolysis and alkaline hydrolysis would give? What does acid hydrolysis of an ester? I bet this should be R prime. What does the acid hydrolysis of ester produced? It's not a salt and water in this case, but a carboxylic acid and alcohol. Alcohol. Remember, when you say you do acid hydrolysis, it means you are adding dilute HCl, okay, and then you are heating the ester. In this process, H plus is acting as a catalyst. It will split, so the H plus will come over here, and it will chop this into two halves, and it will stuff the H2O, which is actually H and OH, back inside the ester bond. So the H is returned to this group. The OH is returned to this group. So based on the instruction provided, can you predict the product on the right? When you force the OH group of H2O back into the RC1O, what will you get? RC1O OH. And when you force the H back to the alcohol part, you will get the ROH. Yes, ROH. You see? So this is an alcohol, which is why we say acid hydrolysis of an ester will give carboxylic acid and alcohol. So this is the carboxylic acid and alcohol. Okay, we have acid hydrolysis. Now we look at alkaline hydrolysis. Because saponification is actually a type of alkaline hydrolysis, we will add sodium hydroxide. And this time around, sodium hydroxide is a reactant. Okay, unlike acid hydrolysis, where H plus is a catalyst. So I'll help summarize it in here. In acid hydrolysis, we add acid. The H plus is a catalyst. It is not really a reactant. Okay, it is the H2O that is the reactant, because the H2O forces itself back into the ester bond. Yes, splitting up the carboxylic acid and alcohol. Then we have in alkaline hydrolysis. In alkaline hydrolysis, the OH minus that you add is not just a catalyst, it is a reactant. As it itself takes part in the reaction. So how does it work now? We treat OH as two separate things, remember? O minus and H. We treat it like that. And we'll put the O back into here. And we'll put the H back to here. So can you tell me what would be the products?
RCOO minus.
Yes, and
alcohol.
And an alcohol, yes. RCOO minus and an alcohol. So you see an alcohol is common, okay, to both acid hydrolysis and alkaline hydrolysis. But then the reversibility of the reaction is different, that you need to know. Alkaline hydrolysis is complete, it's 100% completion to the right. That's why a single-sided arrow. Acid hydrolysis is incomplete. Yeah, they may ask you to compare and contrast these two processes. Okay, now you know. So can you put down how is alkaline hydrolysis carried out? We use a base. Okay, so we have dilute NaOH and heating. Okay, so in this process we are providing the OH minus. Yeah, but the OH minus, because it's a reactant, we don't write it on the arrow. We write it in here. We write it as a reactant. You usually write something on top of the arrow when you have when there's a catalyst like that. So
Sir, how do you call the ion?
Oh, carboxylate ion. Yes, I'm about to write that actually. This is carboxylate. Remember, ethanoic acid. Ethanoic acid can react to form what kind of salt? Ethanoate. So if they change the question and ask you, what is the name of the salt formed by sodium hydroxide and propanoic acid? Sodium propanoate. Yeah, let's do some form of first. Sodium propanoate in that case. So what about this one? Can you write out the formula of the salt? So this is a base, and this is an acid. You remember that acid and base form salt and water. Okay, so the water part, it will always be there. So I don't need to ask you that. But this is the salt. I wanted to give me the formula of. What is it?
Sodium propanoate.
In this case, this is ethanoate. Yeah, because you have two carbon. So sodium ethanoate. So for naming, I'll write lowercase. Sodium ethanoate. F because of two carbons present. So similarly, when you have KOH plus CH3CH2COOH, what would the product be?
Potassium propanoate.
Potassium propanoate this time. Can everyone follow? Yes, CH3CH2COO minus. Okay, and then K plus NH2O. So this is potassium propanoate. So propan, this is an A, okay, no way. You don't call it pro-P, no way.
Can we just like write directly without the minus and the plus?
You better write it, because if you do not write it, you will just trick yourself later. Because if you just write a CH3COONA like that, a lot of students would then later, when asked to draw the structural formula, they would do something like this. They would do something like this. This is terribly wrong. Because if you don't put down the charge, you're just fooling yourself into thinking that this Na is covalently bonded to O, which it is not, okay? So you have to indicate the charge to tell others that, well, yeah, the CH3CONA is the CONA bond. This ONA bond is not a covalent bond. It is an ionic bond, yeah. It is an ionic bond. So Na plus.
Okay.
So maybe take out two highlighter. You can highlight where the covalent bonds are at. These are the covalent bonds, obviously. But this one here is an ionic bond. So this one, okay, is an ionic bond. So you have all these to be covalent bond, and this one is an ionic bond, which reminds me of a question from Form 4. I mean, not raised by Form 4 students, but a student from Form 4, they will ask, okay, or yeah, they will see the exam. Can you tell me how many different types of bonds, types of bonding is present in the compound NH4NO3? What's the name of this compound?
Ammonium nitrate.
Ammonium nitrate. Can you tell me what are the different types of bonds present in? I mean, I don't mean NH bond, I don't mean that. I mean whether there's ionic or covalent bond in here.
Ionic
So ionic,
bond.
ionic bond,
Yes.
covalent bond. The answer is both. Okay,
Oh.
because you have NH4 plus. This is a trick question in DSC. They will ask you what are the types of bond present. They will say, oh, 1 is ionic, 2 is covalent, 3 is metallic, and then you know 1 only, 2 only, 1 and 2, 1 and 3, something like that. So you have actually both covalent and ionic here. So be careful. Between the ions, you have ionic. But within each ion, you have covalent. Do you get me?
Oh, yeah.
Yeah, so if you think you will make this mistake, okay, I'll write this down. What are the type bracket S of bonding present? Okay. The first one is ionic only, ionic bond. So number 2 is covalent bond. And the answer is 1 and 2. Is that clear?
Yep.
Okay, right. Now let's move on. If this is how alkaline hydrolysis works, okay, we can do this onto the ester now. Okay, so let me copy the structure here, and I'll paste it onto the next page. Right, so we have this here. When we do alkaline hydrolysis, okay, or just OH minus or Na plus and OH minus. Yeah, let's just write NaOH, sorry. Okay, we'll write free NaOH here. Because one ester bond, in order to hydrolyze it, it will take one NaOH. So having free ester bond will mean we need a total of 3 NaOH. Okay, so you can just write 3 NaOH here. So the Na and the O, they will add themselves, okay, onto the this part of the molecule. Okay, so you can draw this now. You have C, C, C. You have the OH, OH, OH. You get back the propane 1, 2, 3 triol, aka glycerol. The other part is what is interesting. You get a very long tail, and then you have C double bond O, and then you have O minus Na plus. So this is COONA. This is the part that forms soap, okay, or the soapy detergent. Okay, so this is the part that forms soap, and you get 3 molecules or ion, I should say, of these. So do you see what is happening now? I'll take out two highlighters again. You have the NaO part, which went here. And then you have the H part, which went here. And effectively, hydrolysis means you are cutting off the molecule at this part. You're splitting. Yeah, lysis. The word lysis in hydrolysis means you're breaking. You know electrolysis. Okay? Yeah, you know other types of lysis, hemolysis. Okay, in biology. Okay, the breakdown of blood. So lysis means to break. And therefore, alkaline hydrolysis means to use a base to break the ester bond. Okay? We can understand this literally. So alkaline hydrolysis of fat is equal to saponification. You know the word saponification is where the word salt comes from. Okay, so it's just the rearrangement of these four letters in here. So saponification, the making of salt, means to lyse, means to break the ester bond in fat. Remember, this is fat. Yeah, by a base, by an alkali, in this case NaOH. So you can understand every aspect of this definition. Okay, so base, there's an NaOH involved. I mean, not just one, but three. And then there is also the splitting. So the splitting, the part where I drew dotted line for. And the ester bond, so this is the ester bond. Okay, the thing I circle in purple is the ester bond. And this whole thing is fat. So this whole thing is the fat. Is that clear? The result is a sodium salt. Okay, so you get, this is the most important part. So we have sodium salt of the fatty acid. Because this is a very long phrase, right? Sodium salt of fatty acid. We'll just call it salt. Okay, so this is just salt. How does this work as a salt? Well, we take a closer look at each of the molecules here. So how does soap work? Okay, so how does soap work to emulsify fat? So everyone should have experienced shaking a mixture of oil and water. You know, at first, you may think that you succeeded in mixing oil and water for a few seconds, but before you know it, the water and oil, it will separate back into two layers because of the density difference. This means water and oil, they cannot form a stable emulsion. Okay, so what is an emulsion? So EMUL. Let me put out this introduction experiment first. So you have water, you have oil. Okay, so you are adding oil onto it. You can try this tonight if you think you can mix water and oil. So this is H2O, and this is oil. When you mix water and oil together, they will form
a layer. Two
layers. Yes, we call this immiscible mixture, or a heterogeneous mixture, because there are two different phases. Okay, there are two different phases. They don't get mixed. We learned the word heterogeneous in the equilibrium chapter. If you shake it, you will temporarily get a very unstable emulsion. Okay, emulsion is the suspension of liquid in another liquid. So you have two liquids in here. One liquid is oil, the other liquid is water. So write down the name. Emulsion. So emulsion is a suspension of one liquid in another. So one liquid in another liquid. So let's call it liquid 1 and then liquid 2. Okay, another liquid. So one liquid, let's call it A, in another liquid, let's call it B. So in this case, A and B will be oil and water. Okay, so A and B are water and oil. So water and oil. So you see, without detergent, this emulsion don't last, because after a short while, it will return back into this state. Okay, so this is without detergent or soap added. So from now on, I will use detergent and soap interchangeably. Okay, they mean same thing, okay, in this context. So without detergent. But if you have this mixture, and then you add some soap onto it, which you can also try. Yeah, so fill a bottle with some water and oil, and then try to add a few drops of those heavy-duty soap. Okay, so this is soap or detergent, and it will foam up, okay, or lather up, okay. Yeah, and then it will form a stable emulsion. So you see a lot of like bubbles in there. So the foam is lather, okay, or bubbles, you can say. It means the same thing. So, and in this case, you get a stable emulsion. Yeah, no matter how long you let it sit, it won't separate back into water and oil. You can try. Yeah, so you can see that this emulsion, it will not return back into the original state. That means it will form a stable emulsion. So can you put down without detergent, an emulsion cannot form permanently. Okay, so this is an emulsion. It only happens very briefly. Eventually, it will return back to this state. Okay, so this is a temporary emulsion. So an emulsion, a stable emulsion cannot form. So a stable emulsion cannot form without detergent. Just try it, okay, you will know. But then, when you add detergent, with detergent, a stable emulsion can form. Because we know it will not return back into the original state, okay? It doesn't go back. Yeah, it doesn't go back to this state. That's how we know this emulsion lasts, okay? So a stable emulsion can form, as this doesn't happen. Okay, so because this doesn't happen. So we need to understand the chemistry of this. How does detergent help disperse the oil in water? How does detergent make these two things that normally are not friends to make friends? Okay, you know, water and oil, they can't be more extreme, okay, things, right? So on the opposite side, we look at the chemistry of this, and trust me, it is easy, okay, to understand. When you look at the molecule here of soap, so this is the detergent molecule. So detergent molecule. We have two parts that catches your attention. There is the COO minus part, okay, but the Na plus is just a spectator ion, so you can ignore it. So this is, you can say, a spectator ion. So it is ignored. Yeah, when you look at the detergent molecule, so this is the detergent molecule part. It has two sides. It has a hydrophilic head. So this is the hydrophilic head. Okay, if you have learned the phospholipid in biology, you know the phospholipid is also a similar molecule to detergent molecule. So can you circle this part in the color, and then circle the other part in the color? To me, it looks like a tadpole. Okay, it looks like a tadpole. And this tadpole has two parts. It has a hydrophilic head. Let's see why it is hydrophilic. It's hydrophilic because it's charged. It's charged. Okay, and water, you know, is a polar molecule. So, so this is hydrophilic head. Why is it hydrophilic? Because it is charged. Doesn't matter what charge it carries. As long as something is charged, it can dissolve in water well. Remember how we turn aspirin into soluble aspirin, right? We add sodium hydroxide to try to turn it into something charged, turn it into salt. So it is not water soluble, the head. But this molecule is schizophrenic because the head wants to dissolve in water, but the body does not want to. Okay, that's why I call it a schizophrenic molecule. So you have this part. We have the hydrophobic tail. Why is it hydrophobic? Because it is mostly hydrocarbon. And you know hydrocarbon, the bonds in hydrocarbon CC and CH, are they polar or non-polar? CC and CH bonds. They are non-polar. Okay, being non-polar means it is fat-like. Okay, so you can write down CC and CH bonds are non-polar. okay, making this molecule behave like fat. So making this molecule behave like fat. So this is a rather unusual molecule because it has two things combined into the same body. It has a fat-like body, a water-loving head. Okay, it's schizophrenic. When we add this into water, something interesting happens. Okay, so this is a beaker of water. So when you add this onto water, so you have water here. How would the molecule arrange itself on water? Well, they will do something like this. If you add a lot of detergent in the molecule, let me ask you something first. Which of these parts, the head or the tail, will want to go into the water? The head, because the head is hydrophilic. Remember, philic means love. So you may be asked to complete this drawing. So let's do this. The head will all be inserted in the water. The tail, where does it go?
In the surface. On top of water.
On top of water, because they all hate water. They will stay away as far away as possible from water. So they will look like this. Yeah, chances are that they will ask you to draw this. Okay? Yeah, so they will have, the head is in here. The tail will try to orient themselves as far away from water as possible because they hate water, remember. Now, something interesting happens when you have, let's say, like a surface. So this surface has some oil on it. So it has maybe this is your dish, okay, after you finish dinner. So this is oil stain on a surface. What happens if you add detergent into it? This is oil. Oil would be friends with which of these parts? The hydrophobic tail. If you hate water, hydrophobic means you hate water. Your enemy's enemy is your friend. Okay, yeah, when you can say that this part loves oil and this part hates water. Opposite can be said for the hydrophilic head. The hydrophilic head loves water, but it hates oil.
Why they can't combine together when they have different interests?
Yeah, they have different interests. Yeah, why are they on the same body? Well, this is why I call it schizophrenic. Okay, maybe you can explain to me why schizophrenic, if you want schizophrenic, I don't know. Okay.
Yeah.
But nobody wants that, of course. Okay, but anyway, we have, this is the oil stain. Can you show me what happens when I throw some water onto the oil stain and then I add some detergent onto it? Okay, so let's say I'm adding a few molecules of detergent onto it. What will happen next? Okay, so let's see. We have the oil stain here, and this is like the water tank. It's filled with water now. And then we have the oil stain. Can you show me where the head and the tail will insert itself into? The tail first. Where does the tail go? In the water or in the oil?
In the oil.
In the oil. So you'll see something like this. The tail inserted itself into the oil like that, and the head, because it loves water, it will expose itself on the surface like that, right? And interesting, when you do the dishes, you don't just put the dish under the water and just let it sit. You do some rinsing, right? You will move things around, right? And this action will split up the fat molecule, the oil molecule, into small parts. And more detergent would add themselves inside. So what would this do? Do you remember what is the charge of the head? Negative. Do you like charges attract or do you like charges repel? Like charges. Repel, yes. So this is why as more and more detergent joins, you see these are the newcomer. When more detergent joins, look at the head. Okay, we will zoom in really, really closely now. You can see that the heads, they are all negatively charged. And because all like charges repel, they will not combine again anymore. This is why, have you ever noticed that when you do the dishes, the dish can only get more and more clean. It will not get more and more oily. It will always be less and less greasy. That's because the oil, once they become separated by your rinsing action, they can never recombine. Yeah, they can never recombine. See. So this is one part of the oil. Wow, and this is the other part of the oil.
So much chemistry here.
Yeah, because in here, this is negatively charged, each of them. There is strong repulsion rather than attraction between them. So over time, if we repeat this process many, many times, I split it into half, and in half, and in half, over time, what do you get? you get a stable, what is that E word, that describes a suspension of liquid in another. Emulsion. Emulsification is the action, okay, of forming an emulsion. But yeah, it's close. So can you draw this in here now? We have the, you just have to understand the chemistry. So you have one oil droplet, another oil droplet. When you do this repeatedly, there will be so many, of these small oil droplets form, okay? Yeah, that they cannot recombine again. So this is negatively charged, this is negative, this is negative. So the whole thing will form a stable emulsion. So do you see the chemistry in here? Yes, okay, yeah, don't worry. They will really just ask you to describe the two different parts of the molecule. Which part is hydrophobic, which part is hydrophilic. You just need to know that the head of the COO group is the charged hydrophilic head. And the part with mostly hydrocarbon, it is the hydrophobic tail. Okay, and the hydrophobic tail will interact with the fat molecule. So let me just write this down in here. Yeah, over time, so agitation, meaning you shake things around, will break the fat molecule up. And over time, when done repeatedly, an emulsion will form. Okay, so an emulsion, emulsion, will form. So is this clear?
Yep.
Right. So then I think we have in this chapter only the nylon and the polyester left. Okay? Yeah, so that's quite some chemistry. Make sure you finish the organic synthesis question. I uploaded the answer sheet to the group. Okay, so check that. Okay?